Swayam Prabha. Digital India. Educated India.
So this is our last class, at least with me. You will have a full day as well. But what I want to do today, you will have also slides about the design of tunnel segments, of structural robustness. But what I want to focus on today is we have seen yesterday some examples of design of single connections. How does this translate into, well, this was a mock-up building, so it was not real one very big, but was still a mock-up, and was a mock-up that we designed and tested, especially for earthquake resistance of the wall system. Well, the sides here are not readable, are quite small, but I can tell you this span here, this span here was 8 meters. So we had, you see, a structure which had beams in this direction here. Okay, so they were like 3 parallel frames. Okay, and the frame worked like this. Between these 3 parallel frames, 1, 2, 3, we had these roof elements laid out that were separate. Actually, also this span, this net span was 8 meters. So 8 meters mean from center axis of the column to center axis of the column. Okay, so if the span is 8 meters and the roof element are 2.5 meter wide, it means that you have 3, you have just a small gap in between, but it was okay. They were not connected between themselves, so there was a gap. So the roof elements were discrete elements. Okay, they were 8 meters long. So imagine 2 modules 8 by 8. The columns were, I think it was 5 meter high, something like that. Plus there were the 65 centimeters of the beam plus half a meter of the roof element. So everything was on top of each other. And in some cases, in this direction here, we also had the cladding panels. Okay, so this was the structure mock-up. Then we built up a, twin mock-up. The dimensions were the same, but simply, in this case, the beams were in this direction and the roof elements were in this one. Why this? Because we tested these elements here. Here there was a reaction wall, and we applied a horizontal force. So it's like if you have the same building, but you want to see whether the horizontal force comes in one direction rather than in the other. Okay? So first of all, let's start with the design of the columns. We had these 400 by 400 square millimeter columns. And since we had to design for seismic regions, the provision is that you add 1% longitudinal reinforcement area ratio. So this means that you must have 1,600 square millimeter of reinforcement minimum. And you can easily do with 8 16 millimeter bars. These are also, you can see here, also the arrangement of the stirrups. You have one outer stirrups, which are circular, and you have one internal one. Well, as a matter of fact, here, what does it happen? But this is not much different from what happens in precast building structures. You see, we analyzed this mock-up building, and we calculated the load which goes on each single column. Well, you can see that more or less central columns take not exactly twice as much, but more or less like that, because you can easily figure out if you have this building here, the beams are in this direction. So this column here take the load from half on the left, half on the right. In this other case here is similar. Simply in this case, the weight of the beams is equal everywhere because the beams are like this, and you share the columns. But what is important to realize is that if you divide this value here, okay, this is the axial force. You divide by the area, you make this calculation. You calculate this parameter here, which is ni, which is actually the value of the axial force divided by the area of concrete. Well, actually, you should divide it by NRD, and NRD is your resistant axial force, which is the area of concrete FCD plus the area of steel FYD. Okay, is the maximum axial load of the column. You see that these columns in this precast mock-up, they were very lowly stressed, just a few percent of their capacity. Well, actually, this sometimes happens in precast building structures, because these elements here have to be designed also, especially when it comes for earthquake, have to be designed for maximum drift. And maximum drift is 1%. So we did the calculations, and actually with these sides, we were exactly at the very limit. So you see, we are at the limit of the serviceability limit state for the service earthquake, for the earthquake design. But we have plenty of margin for the axial capacity because we are just engaging it. We are just engaging it a few percent. What does it also mean? That, are you familiar with bending moment axial force interaction diagrams? They are something like this. So you see that there, probably you plot in the other way. Well, but it's just look at it, tilting your head. But what does it mean? That it means that in precast structures, we are likely in this region here. Well, this is a good thing and a bad thing. The good thing is that we are in a region where if your axial load increases a little bit, your bending moment capacity will also increase. So it means that you have some extra, reserve capacity. The other thing is that, the axial force, if it depends on the dead load, is that one. So it means that you are really not exploiting the best moment capacity. So you have to rely upon a lower one. But that is the situation. So this is what you have to do. And what we did at this point, well, the very simple, because here, we had to design the experiment. So we had to come up with very simple numbers. And we said, okay, I know that my column will behave like this, okay? So my bending moment at the bottom will be capital H times 8 of the column. What is the maximum value of the H force that I can, and there is the axial force as well. What is the maximum value of the H force that I can have? Well, the maximum value of the H force comes from this equation. when the moment at the bottom edge cross section reaches its maximum, that value corresponds to the maximum axial force. So simply, H max is MRD divided by H. My structure has 6 columns with different, yeah. So I simply calculate the maximum force that I can give to the structure as the sum of all the maximum bending moments divided by the height of the column, 5 meters. What is the assumption behind this? Well, the assumption behind this is that if by accident you have a column which by itself reaches its maximum capacity and the other ones have not, they redistribute the load, and so you have a uniform sharing. So in the end, this is something, it's a very important conceptual assumption that we checked. When we redistribute the loads, in the lecture that we did, I think on Monday, it was that, or Tuesday, I don't remember. We said, well, if you have different elements, we take the lateral load, you distribute the lateral load proportional to the stiffness, okay? In this case, forget the fact that sometimes we had the walls. We had only 6 columns, so all the 6 columns participate to the resistance. They are equal, they take an equal share. But this is okay when you redistribute, but when you push it to the ultimate limit states, you can redistribute force proportionally to the strength. And here the strength is not much difference because you have something. So these were the assumption. This number here, you can see the maximum lateral force, was a useful number for us because we had to design the experiment. So we had to say, which is the capacity of the actuators that we have to use in order to apply the force? Because we want to apply, well, we expect this maximum force, which is 16 tons. Since we were applying it with 2 actuators, say 8 and 8, so to stay safe, use 10 tons actuators, something like this. So this is the reasoning that we made. And then, okay, we said, okay, now let's go to design, or to, because then we had also to say, how do we connect the beam to the column to the roof elements? Well, the beam to the column was connected in this way. We had the columns here. You see that these, and these are the longitudinal reinforcement. They were 8. If you look from one side, you see 3 of them. And these are the stirrups. You see on the top of the column and as well on at the bottom, we had stirrups which were spaced at 75 millimeters. 75 millimeters, if the stirrup is 8 millimeter diameter, 75 millimeter is a little bit less than 5 times the diameter of the bar. That is the minimum prescription. And some people say also, well, at the very top and bottom, put even another stirrup in the middle. So do like 3 times the bar diameter. It's very dense. And consider that you have one stirrup like this and another one like that. So really, it's a stirrup every centimeter. But then with a little eccentricity, there are 2 dowels coming out of the bar. 2 because the beam was made like this. So the 2 dowels had to connect the 2 bottom parts of the flange. Okay, and these dowels were, well, we said 16 millimeters. 16 millimeter. Actually, well, we here applied, it was not strictly necessary, but here we applied an overstrength factor of 1.35. So for which value of the force have to we design the connection between the column and the beam? We have to design for the maximum force that each column can take. And this maximum force that each column can take, maximum lateral force, is the total force divided by 6, because we have 6 columns. So we ended up with this value. There is a 1.35 factor. that it's not strictly necessary because our column is our connection is on the top of the column. It's far from the critical region. So here you can also accept a more moderate over design, 1.1, 1.2 maximum. But this is just to show you, that with two 16-millimeter bars, this formula here is what it comes, as I said yesterday. We used the model by Vinci Liu and Tassios for dowels, because this is a dowel. And as a matter of fact, this is what they call the dowel strong mechanism. Strong mechanism is when you have enough material around. And so you can expect that your concrete crushes and you form a plastic hinge in the bar. So you have, and well, this is from their analytical elaboration. You have the paper, you can look for it. But you see, it depends on the square root of the, on the square power of the diameter of the bar. Yeah, because it depends on the plastic bending moment of the bar. And the plastic moment of a circular bar is P divided by 32 times phi squared and so on. Well, it's actually phi cube, but then you have to divide it by a length that you make proportional to phi. And then they come up with this square root of the compressive strength of concrete and of the yielding strength of steel. Well, in this fact, there is some mix of a physical model and best fitting of data. But you see, with a quite good concrete, not exceptionally high, but quite good, because we have SEK 40 megapascal, okay, and 500 megapascal steel, which is customary, we end up with this value here. You can say, okay, I have plenty of strength because I need 38, I give 62. Yes, there is a but. This formula here is for static load bearing capacity. When you go for cyclic, you can expect some kind of degradation over the repetition of the cycles. And prudentially, what the authors of the paper we refer to, Vinci Liu and Tassios, say is 50%, so divided by 0.5. So this means that you have here around 36.2. Well, formally speaking, should not be checked, but you can always say that, okay, if you reduce a little bit that over strength, you put 1.2, you are okay. But you really see here, this was compared to a real precast structure. This is not very, because here we have, okay, a span of 8 meters, you can have up to twice as much. But the column is just 5 meters. And it's 400 by 400. In precast structure, you can have twice as much. So you can expect even higher forces. And you can say, okay, I have two 16-millimeter dowels. They are already some, decent bars. But still you are at the, very strict limit of the connection design. Because, the important thing is that there is this value formula. We do not design for the force that we expect. We design for the force which will correspond to the failure of the critical cross-section. And we require some overstrength on it. What does this physically mean? This means the connection will not break absolutely, because before you have to, fail at the bottom cross-section, but you still have some overstrength. And why this? Because the fundamental assumption is that all the 6 columns participate into the resistance. This means that you have the diaphragm action of the roof deck. But this roof deck was made by 3 beams and 3 plus 3. Yeah, so it was something like this. So really, the diaphragm action, as we have seen in the model yesterday, is all due to the connections. If one of them fail, you will start having that this element here moves strangely. This is mock-up here. So this was an interesting example. I remember it because I was put to work on this exactly after finishing my PhD. And my PhD was on numerical modeling, was fracture and damage mechanics. So it was likely a jump into a pool, and I had to learn to dive. That was. So this was, you know, the design of the beam to column connection, which is the design model that we use for the roof element to beam connection. Well, for the roof element to beam connection, we used that model that we have seen yesterday, and we said, okay, if you have a force here, you will have here at the four, well, probably they will, yeah, you know, you can say if the force comes in this direction, you can expect this to be reaction forces, so let's put them in this way. So it will be like this. But you will also expect, so you have to give a negative bending moment, so it could be something like this. You will also expect some forces in the you know, direction orthogonal to the force, because the diaphragm action gives you this in-plane motion that you have to counteract. You have the scheme in the slide, well, in the same packet of slides, but is the model that I showed yesterday. Well, but then your connection will be asked to resist a force, which is actually like this. So you know, use the vector rule. No, nothing. So also the lateral chord action is demanded to these connections. So for this reason, well, you see, because this is a force which goes on a single dowel, so you are requiring this dowel to take more than 2 tons and so on. So it can be a huge demand. You just rely upon these dry connections. And the other fact is that the force, you see, the force here is not applied at the level of the beam roof element interface. Since it's an inertia force, you will apply in the center of mass, because the inertia force, as we said, is an effect of the earthquake, which comes from the mass times the acceleration induced by the earthquake. So it's applied where the masses are applied, and the masses here are applied in the center of most of the masses on the top. So this also has this uplifting effect on the column, which means that the connection, since this action is cyclic, can come one way or the other, you have also to check the connections for some, you know, pull out from the beam. So we use it once more, because in the end we used a connection like this. You see, we had these steel angles and we had dowels. I don't know if we have some other drawings here, but actually if you look at this single edge of the roof element, the connection was made like this. We had 2 steel angles, and we had a dowel passing through. Obviously here we left a hole, and you had anchor bolts going here. So this was the detail of the connection, and here you see it on the side view. But you see, actually we had here a 500 millimeter wide beam, so half a meter wide beam, a little bit wider than the column. So we provided the column also with a little corbel at the top to accommodate, because the column was 400 millimeters. But you see that, well, it's not that you have plenty of space, because you have to accommodate here 2 roof elements. So it means that from here, it means that from here to here, you have 250. And we put this all here, we made in such a way that it was exactly in the middle, 125 millimeter. Well, you know, if you think of using for dowels, 16 to 20 millimeter bars, it means that the clear space that you have here is about 110 millimeters and so on. So it's a little bit more than 5 times the diameter of your dowel. So you say, oh, I have half a meter, I have plenty of space. No, then when you go with the sizes that you have and the fact that you have to guarantee a minimum, you know, concrete around, it's not that much. So this is a very important, you know, reality exercise that you have to make when you design the connections. Because since in our schemes we make reinforcement as small circles, it seems that we have infinite space, but it cannot be like that. Yeah. Actually, we used something similar to expansion anchors. We're not, in this case, we're not embedded bars. The beam, thank you for the question. The beam was drilled when it was on the ground floor. And then we installed the expansion anchor. They were one of the major commercial producers of this expansion. Yeah, I don't remember whether they were Hilti or Fisher, but was one of them. Yeah, I don't want to say which was, but I remember. I think it was Fisher in this case, because I remember that, you know, we asked them, but we needed, how many do we need? We need 30 dowels, 30 anchor bolts. So they said, well, we will give you, but you have to come up to pick them up, because for us shipping is more than the cost. And obviously, you know, this was for a research purpose, so we didn't buy them. We, you know, were given for free provision, but they said you have to come up and to pick them up. So I went with the car and with these boxes, because actually, you know, each of these anchors can be quite heavy, and these steel L pieces, we made them very strong, so they were 1 centimeter thick, so they could be very heavy. So was not. Well, here we repeat the same calculation, but you see, which are the failure modes? Well, first we have the dowel failure, the anchor bolt or the bar. Then we have the spalling of the concrete, beam or column edge, depending on where you are. And then we can have the failure of the cross section of the beam or of the column, the pull out of the bar, and the shear failure. This order of failure mechanism is not casual. Dowel failure, since it's due to a plastic moment in the dowel, is actually here is the only plastic mechanism that we have. So that is the one that we would like to occur first. Then spalling on the concrete. Well, spalling of the concrete, it's true that it's a brittle mechanism. Why and how it does happen? Because you have, you know, at a certain point, if this is the dowel bar, okay? This dowel bar pushes here against the concrete. So you have here and you have this. And what it happens is that you form a crack like this. So the maximum force, it's very easy to be computed. You have estimate about this width of this, which is a certain, I say, alpha times the bar diameter. And you say, well, at the maximum, at the ultimate limit state, I will have fully cracked. So maximum value is when there is tensile strength everywhere. A stress, tensile stress equal to the strength. So you calculate tensile strength times the length of these two segments, project in the direction of the force, and you have your maximum force due to this mechanism. This once more to bring you back that, okay, you have the connection, interpret the stress transfer mechanism, hypothesize the failure mechanism, and then it's very simple stress model, and you know, you are just to use equations of equilibrium. Well, you cannot avoid this failure mechanism, but you know, you can provide it in some way, some kind of ductility, because you put some extra reinforcement there to tie that cover of concrete around. Bending failure of the cross section. Well, this is something which comes out. Pull out of the embedded dowel. You don't want it to come out. And sliding shear failure you don't want, because sliding it's shear and it's a brittle mechanism. So you have them in this order. And here, this is, for example, the bending failure of the beer cross section. This is a typically design of a reinforced concrete cross section. You simply do that. This is the dowel failure according to the model that we have seen before. Well, you see here you have 1 minus alpha square. Well, this is because you can expect in the dowel some tensile forces because of the tilting action. And so this is the same formula that you use for bolts when the bolt is subjected to shear and tension. So really, as I was saying yesterday, there is nothing new here. And this is the pull-out failure. Development length times pi times the diameter of the bar times the bond strength. And you want the bond strength, the strength of the bond mechanisms to be higher than the yielding of the dowel, because that is what you want. So really, these are the numbers that you have. And that's exactly the same thing we repeated for the other direction. I will go quickly through this because these are just calculations. You can follow them. What I want to show you, because I think this is more interesting from a, not only a research perspective, but also a, applied R&D perspective. Now let's hope that this can come out. And we have not blocked it too much. So the purpose of this, like the purpose when you design a connection, is that your structure must work. So this was our structure mock-up. You see here, well, the picture is a little bit bigger. You see, these are the columns, these are the beams, these are the roof elements, this is the reaction wall, and these are the actuators. And you see here, in order to apply a force which mimicked in some way the diaphragm action, so you had to impose equal displacement, we needed here 4 actuators, and you see here there is also some kind of rigid link which connected to the central roof element. So we wanted really a uniform displacement of the deck to be applied. And as a matter of fact, you can also appreciate there, as I said, from here to here is 5 meters, plus you have 0.65, plus you have 0.5. So from here up to here is about 6-point-something meters. And then there was this foundation element. I remember it was more or less like this. So it was about 1.5 meters. So total 8 from ground up to top was about 7.5 meters, a little bit more. You see how slender the column is. So you see, really appreciate those 400 by 400 square millimeter column is really very, very thin, very slender. Just to appreciate that. And here, well, this is a little bit, darker. You see, this is the other assembly. We had the column here. You can see the beam and you can see the roof elements. In this other direction here, we only needed 2 actuators, but they were connected to all the 3 roof elements which were laid down in a series. Well, these are the models. I just want to go through tests. So what we did in this lab to validate, this was mostly a validation of the connection design methodology in a sense. We did what is called a pseudodynamic test. What is a pseudodynamic test? When an earthquake comes, this one here is a partially artificial earthquake. What does it mean, partially artificial? It means that it starts from a real recorded accelerogram, which was one of the accelerograms which was recorded in 1976 during the Northeast Italy and Slovenia earthquake. But then one important thing is also the frequency content of the accelerogram. And as a matter of fact, natural earthquakes, the frequency content is whatever it is. So there are procedures to enrich the frequency content of a natural accelerogram, so to make it spectrum compatible. The spectrum is what we use in the design codes to design for earthquake, and is actually a diagram like this, which gives us, for the period of the structure, gives us what is the acceleration that we can expect. Okay. Well, the interesting thing, as I was repeatedly saying in these days, is that precast structures generally fall in this region here. And so you see, with respect to the peak, you have a significant lowering. This is not the case, for example, of cast-in-place precast structures like this. These are industrial frame structures. If you go for cast-in-place building structure, the rule of thumb is that the period is more or less the number of the stories divided by 10. So it means that up to 5 stories, you are in this region here. So where you can have strong acceleration. Up to 5 stories, the building is actually quite stiff, quite squat, because 5 stories is 15 meters. But you can easily imagine that you have a building which is 15 by 20, 25 meters. So it's more or less like a cube. And the cube is very, very squat and very rigid. Only when you start going higher, you start having some, it's not exactly dampening, but you reduce the effect. So and what is the pseudodynamic test? You see, this accelerogram, this is the real earthquake. The most intense part is 10 seconds. Whoever of you has experienced an earthquake, it's like that. You start feeling it, but the moment you start panicking, well, luckily, if you have experienced an earthquake, and we are here, we have experienced an earthquake where we could start panicking, but then the earthquake was over, and we were safe. I don't remember this one because I lived quite far away. I had relatives there, but I remember there was another very strong one in 1980 in southern Italy, and I remember it pretty well. That was quite strong. You could hear the window glasses to tremble. You could see the chandeliers really to pendulum and so on. But so that lasts 10 seconds. Well, it means that you perform a very huge, and then your test is just 10 seconds. And this is what happens if you use shaking table tests. It takes months to build up the model and so on, and then that's over. And then it's other months to elaborate all the data because you put the sensors and so on. What does the pseudodynamic test make? Actually, they are based on the equation of motion which is like this: m times the acceleration x dot dot plus the dampening coefficient c x dot plus the elastic response equal to f. The f is this, okay? And so what does it? You start, assigning the first step, and you record the elastic reaction of the structure. Then you integrate that equation, and you compute what is the next step that I have to give. So this one here lasts 3-4 hours because it's a very, very slow process. But, well, the thing is that you really simulate an earthquake applied to the structure. The drawback is that you lose the strain rate effects in the strength of the material. But generally speaking, strain rate effects are beneficial to the strength, because we say that if loading and action comes with a very high strain rate, the stress waves do not have the time to find the weak path. So it can have generally, if you perform, for example, like dynamic test on materials with the split Hopkinson bar, the strength that you get is higher than the static strength. That we have the dynamic amplification factor. So you have, pros and cons. Well, I could say that really, if you perform this test for very low earthquake, it's really boring because you don't see anything. But when you start going, for little bit stronger earthquake, you really start seeing the structure moving. And I can guarantee you that, you have something like 8 meters on the top and you see it moving of 10 or 20 centimeters. It's really interesting. And there is always the safety responsible, which always shout at you and say, don't go too close, don't go too close, and so on. But that was a, nice experience. If you will ever have the chance to go and visit a lab like that, it's a very nice experience. So we performed this test at 3 levels of the earthquake. This is the peak ground acceleration. So is the maximum acceleration of the ground that we expect. 0.14 G, 0.35 G, 0.225 G. Why this? Well, because more or less, even now that the seismic design code has become much more, rich, this was the peak ground acceleration that we expect in what we call it seismic zone 1 in Italy. So we're the most severe. And actually northeast part of the Italy is like that. And then the southern part, Calabria and Sicily, the tip of the toe of the boot and so on. This one. This one here, if you look exactly, is this divided by 2.5. It's what in the code is assumed to be, if this is for life safety, this is for damage limit state. So this is for ultimate limit state, this is for serviceability. Actually, this one here was 1.5 times this. Because actually, the interesting thing is that since these structures are very flexible, and the columns, as you have seen, they have plenty of strength. Actually, if you compute the theoretical earthquake resistant capacity, they can resist earthquakes up to 1 G. What does it mean? It means that you have the building with its own weight, put it like this, and it will resist its own weight, but acting as a cantilever. So it's very, it's not common. We have to say that, for example, there was an earthquake near Naples a couple of days ago because of this bradyseismic motion and so on. And they recorded, interestingly, only very, very near to the fault, because these are very superficial earthquake. So very near to the source was 0.4 G. But 5 kilometers away was 0.005 G. So it was very, very low. We had earthquakes where the peak ground was 0.7 G. So it's not, rare that you can encounter this. And you see, what did we measure? Well, the first thing that you measure is the force that you are applying versus time. And these are the displacement that you record versus time. Okay, that's fine. But then, what we did, where is that? Okay. What we did, we went and we calculated, because we designed this structure to have perfect diaphragm action. And how can you guarantee the perfect diaphragm action? Well, we have seen yesterday, perfect diaphragm means that all the frames, they displace in the same way. So we calculated the ratio. We calculated the ratio between the central column and the outer column. And you see that here, 0.14 G, well, this ratio is close to 1. So that was okay. That was okay. What is the other graph? Look here. In this case here, we have also the claddings. And what did we do? Well, that was quite demanding. Was a huge cost for the experimental campaign, because the history, the sequence of the test was like this. We performed, first of all, you generally perform a test at very few percentages of the peak ground acceleration, like 0.05, just to check all the instruments. So we did that, and that is linear elastic. You don't record almost anything. Then we installed the panels, and we performed the test at 0.05G and at 0.14G. Well, if you have the panels, what does it happen is that the frame close to the panels stay almost fixed, and the central one have a larger displacement. And you see with the claddings, which are these hollow markers, you see that the ratio between the central and the lateral columns was 3, and then it stabilizes over 2. So the claddings, they alter the diaphragm action because they act as very stiff elements. But then after having performed the test with the panels, well, 0.14G, you are still elastic. We removed them. So that was the huge cost because a company had to come with a crane and first install them, and then we called them and say, take them out and put in the yard and so. But you know, this is also to show that, you know, this was a research intended to support the codes and was funded by European Commission, so it was public funding. So this is that having that code which says something that nowadays all the engineers use requires investment, and it has to be public investment. But there was also private investment because companies provided us for free the elements, the transport, and so on. So it was a really pool of efforts. But you see, after we removed the panels, interestingly, we got back to the diaphragm action. And we did this for all the tests. I think there is a paper published on this, so we had that. And these are the response, elaborated in terms of force displacements on the columns. So you see at 0.14G and 0.14G, here is the cracking point, and you just go a little bit higher. This is at 0.35G, you had the cracking here, and here you are just at the theoretical one set of yielding, and you can see some, you know, plastic response when you go up to higher level of earthquakes. Which was the effect of the claddings? Well, the effect of the claddings here, it's evident. With the claddings, you have maximum displacements of 20 millimeter in the central columns and even less in the outer ones. Without the claddings, you have much more similar displacements, but you see that they can go high up to, you know, twice as much. So the building was much more stiff with the claddings. But which was the effect? Which was the effect of the cladding or not on the connection? Well, I don't know whether you can see here. Actually, these diagrams here represent. Well, let me highlight with the pen. We put displacement measuring sensors like here. Okay, we wanted to measure two adjacent roof elements. What did they do? Because what did we expect? We expected that they do something like this. So we said, if the diaphragm action works, this is what it has to happen. And you see, if you look at these curves, you clearly can see that the two sensors work in phase opposition. So the sinusoidal waves, they are not superimposed. One does like this, and the other one does like this. So when one is going into positive, positive means that the elements tend to, you know, detach from each other. The other one is negative because the two elements, one was here. If these elements move like this, these 2 points tends to go farther, but these 2 points tend to get closer. So this was the proof, in a sense, that the diaphragm action, as we intended it, was working. Because actually you cannot measure, for, as I said, we never measure forces. We always measure displacements. And yeah, they were placed at these edges here. Yeah, here. Yeah, but these are the roof panels, not the, yeah. This is on the roof. The force comes here and here. Yeah, you mean here? Yeah, yeah, they were on all elements here. No, here. Okay, this is the reaction wall. Okay, and this is the structure. So these are the roof elements. These are the roof elements, so you're looking from the top. We place the sensors on each pair of elements. How to say, leeward and windward, if you look. Was the wall diaphragm, was all diaphragm. So this is, yeah, the panel you could consider as rigid in itself. So was the bending of the diaphragm, which you can imagine this diaphragm is made of articulate pieces, and we wanted to see how did they move with respect to each other. Where is that here? And you see here, this is at the end of the tests. We had the failure of the bottom of the column. There was some spalling. Well, you see, this is one stirrup here. This is one stirrup here. This is one longitudinal reinforcement. You see how close are the stirrups here. But you still see, can you appreciate that that bar is a little bit, you know, curved? So in between the two stirrups, when you expel the cover because of that bar is like a beam pinned at its edges, which can buckle, and that it does, and that it does. So you have that. That was outside the footing, because this was the footing, was immediately, yeah, immediately outside the footing, yeah. Yeah. And these you can see here are, you know, the, well, we interpreted because we put, I don't know whether we can see here, no, yeah, it's not. Here there was a crack and so on. We put some measuring instruments on the columns to check the curvature. And so we elaborated moment curvature for the different segments. Each segment was about half the depth of the cross section. And you see, this is the first segment. I think this is the second one, and so on for different things. But you see that already when you go from half the cross section depth above, you know, your curvature is much less, because here you have 10 to minus 1, and here you have 1 order of magnitude less. So you have a concentration of the plastic hinge length. And this is, you know, the development of the curvature. You see, you concentrate it up to here, and then already 400 millimeter is the depth of the cross section. From that point onward, you are in the elastic part. So you have really concentrated your deformation, and so your plastic hinge inside the depth, which is, yeah, close to the cross section depth. This is the final one was the pushover. So we did this, and this was, oh, we did that. Yeah, we did that. Yeah, yeah, we did that, and this was, this was the model that we did. Well, actually here you can also see what I was telling yesterday. This point here is the top of the column. This is the beam. So we had to put a rigid link to take into account that the beam is 65 millimeter deep. So the axis of the beam is 30 point something centimeter on top of the column. This is the roof element in red. And you also see that there are some rigid links that give you the exact position, and so on. So then we ended up with a simplified scheme. And we embedded the plastic hinge length according to the results. This is the model, and we were able, to simulate back more or less reasonably the response. There is foreseen in some cases some residual strains that we are not able to capture. What it happens if you have cracking and you have some local yielding, then when you go back to zero, you do not recover that yielding. So in the reality, you don't recover the deformation, and that is. I think this was very simple. One was an SAP 2000 or something like that. This was done 20 years ago, something like that. But then we wanted to go into this. We said, okay, the simplest way is that we have a strong connection. Strong connection means that this connection is over-designed like we did, and all the dissipation occurs here. What if we have a partially weak connection? So we allow also some energy dissipation to occur here. Or we simply say, okay, let's put the weak point. It's like if you have the base isolation of the roof deck. Let's put the weak point there and have it like that. And you see this, the response is here that you have to model the connection as springs. This is when you have a strong connection. This is when you have a ductile connection. Well, it can seem that, okay, the ductile connection, it's better because you expect less force on the structure. What is the other aspect that you have to take into account? Well, that you have to guarantee these large displacements. But it's not only the connection that has to guarantee them, it's that the seating of the roof element on the beam and on the column must guarantee that. And here you can also see that, this was in terms of maximum drift. So you see, this was to show you how the design of the connection, that is the design of a simple component, it transfers at the scale of the design of the structure. Now, another example of testing on connections that we made was this. There was a company, precast company in northern Italy, in the same region where the earthquake came from, that said, okay, we have the issue of our, facade panels, okay? And facade panels, generally, they are not connected to each other. They simply come they come in a shape like this, more or less, and this is looked in cross section. You install them in a series, and then you have also to put some sealants here because you have to avoid that the rain goes through and so on. And then they said, okay, if we slightly modify this and we shape our panels, for example, like this, can we use this region here to accommodate devices like this, which, due to the fact that these panels during an earthquake motion, they slide with respect to each other, they can provide some energy dissipation. So we said, well, why not? Let's try. And we ended up designing, these very simple devices. Actually, these elements here are steel I-beams cut into halves. So these you attach to the left panel. These you attach to the right panel. And provide this with these slots. Then when the two panels come together, you complete this sandwich. You can have already in some way pre-assembled on the right part. And you have here these two brass plates, and you cover them with steel plates. Yes, metallic dissipators. Yeah. Then a lot of work from this work, a lot of work followed up also. Stefano Pampani did something in Rome as well. Well, why the brass platings in between? Because we went through the literature, and it was said that steel to steel concrete, so because you dissipate here energy basically because of friction, steel to steel very rapidly degrades. Steel to brass is more stable. So we wanted that. And so we performed some cyclic tests only on the device. You see this red is a very stiff frame through which we applied relative displacement like this. And this is the device that we tested. And you can see here, these are the two pieces. You see, these are the holes to install them on the panels. These are the steel plates which sandwiches, and these are the brass platings in between. You see that the damage occurs in the brass plates, but the steel plates are almost integer. And this is the response. Steel to steel, you see how fast the response decreases. Steel to brass, we applied the two subsequent series of 20 cycles. And you see that the first series is okay, but after the second series, already the response is very stable. And in the third series, it remained almost constant. These were cycles of constant amplitude, back and forth. Well, then you can say, but okay, if I, instead of using the plates as they come, if I brush them with a steel brush, or if I use the sandpaper, you see, I improve quite a lot and I make it even more stable, because if it's friction, it depends on the roughness of the cross section. What is the effect of the strain rate? You see, this is at 0.1 millimeter per second. This is at 2 millimeter per second. You can clearly see that if you increase the strain rate, the response of your material, the response of your structure is better. And this is a thermal camera where you see that the energy dissipation into friction basically goes into heat, is dissipated. Well, you have 20 degrees here, and your connection goes up to 40 degrees. Well, if you are in good season, well, you dissipate it. But if it's like now in Italy, where you have 40 degrees temperature, you don't dissipate it at all, so it stays like that. But this just to see. And we ended up with some design guidelines, from the force. We developed a, like a design table for the friction coefficient. So you see that we have friction coefficient between 0.25 and 0.3. And the interesting thing, so sorry, there is no, this is in Italian, but this means steel brass. This is new, 0.28. And this is steel brass. After use, when you rebrush it, you go back to 0.3. So it's something interesting. And once more, we developed a simple design model. So we say, okay, we have a building, total weight of the roof, weight of the columns, snow load, end up with seismic loads. And this is the model that you can end up with. So you have the scheme of your element, you have your earthquake force, and you have a certain number of connections here along the panel edges, which dissipate the force. So you can easily calculate the force that is, asked according to the earthquake to each of these devices, and how can you obtain it, considering that this force is the friction coefficient times the number of the connections times the tightening force that you give to the bolts divided by a safety factor. And so this was quite a simple example that we developed. Another more thing before we conclude, just to finish the explanation, another example of test that we did. Yeah, it was this. So I was mentioning, okay, this is, yeah, I will tell you about this. Yeah. So we wanted to test, this was the column to foundation connection with the column shoes. So we, build up a column block, and this was the connection here. You see, we tested horizontally. This, you can realize this here, this is a jack, and this is the counterpart, was a Dividag bar. I think it was 40 millimeter diameter. So we apply here the contrast plate, and then the Dividag bar passes through a hole here, and you apply here the force. And this is to simulate the axial force that you have in the column. Yeah, it has that, but in this case was not our purpose. That was just to apply the axial force that you expect in the beam. And then we applied this cyclic loading, or this monotonic loading. You can see it here, to simulate the earthquake effect. You see here, these are anchoring bolts, and actually you see here, these are anchoring holes that we have in the floor of our lab. I can probably, yeah, you see, this is a view from the top. Our floor, which is about 1 meter thick, has these anchoring holes. They are arranged according to a equilateral triangle network, and the distance is 1 meter from one to each other. So we can arrange, reasonably flexible arrangement. And actually, if you see here, well, this was an old picture. Now the arrangement has changed, but we had another loading frame here. This was a connection testing device that I will just show it a bit later. So we were quite flexible. So you see here, where was that? You see, this is the column, this is the foundation, and this was the threaded bar which come out of the foundation, and this is the connection device. What happened because of the cycles is that with the cyclic loading, you loosen the tightening, and then you break the threaded bar coming out of the foundation briefly. But before, this is the mortar bed joint that you had, which is cracked. But before, you also were able to have some cracking, which means some kind of dissipation and some transfer of the action from the foundation to the column. The plastic hinge did not form in the column. The plastic hinge in this case was a very narrow region here. Yeah. And these are some elaborations, we did some cyclic tests for the service load, and then we ended up with the response. And this is the theoretical moment curvature diagram of the column cross section. So we could say that the connection was able to give you a response similar to what you would expect from the cross-section column ductility. The issue was that, we realized that actually this connection here, which had some kind of, was equivalent anyway to a cross-section with just four 14 millimeter bars. So the issue is that you have to over-design that connection. So the equivalence in terms of ductility was not that immediate. But this, you are right. This is the self-centering effect that we had as a spurious effect because of that. And the other test that we made, this is the arrangement. Imagine that this is your roof element in the form of a double T, so that is the stem. This is the beam, and these are the connecting devices that we used in the mock-up. So we wanted to do the tests on the connections. You see, these are some sketches. You have these two steel angles, you have this threaded bar going, and you have these are actually like anchor bolts that we use there. And you see, this is the mock-up. Since we wanted to make cyclic tests, we used two actuators, one pushing up and the other pushing down. These are the connection devices. Actually, you can appreciate here the creativity of engineers when they have to make a test in the lab. You see that this block here was made with 1, 2, 3, 4 steel embedded plates, because when we damaged this part, we tilted it and we could use this, and then we could tilt it. So we could use the same blocks actually to make 4 tests. Because actually, you know, casting these elements is not a big cost, but it's a big work. And so you want to reuse them as much as possible. These are some images that we had, and you know, some images here. This was the case in which we had a very, very thick, you see, this is the steel angle profile, very, very thick. And we had this response cracking, some kind of, you know, nonlinear response, but we did not exploit the full yielding of the connection. And then we said, why don't we go? Why don't we go? We had the, you know, failure, the splitting failure of the concrete block. And we said, well, why don't we go? Or I think we do have it here, yeah. Then we went to thinner elements. You can see here, these were actually thin plates which were cold formed in a sense, like this. And you could see here, well, the cyclic response here is much more stable. You go for higher displacement. And you can see here that in this case, the deformation goes into those steel angles. This is the difference, what I showed between a strong connection or a weak connection, which can work. You see how much deformed it is. But what is more important is that while before we damaged the concrete, so it means that you expect damage in your beam or in your column. Here, in this case, all the damage was in the steel. You see the concrete around is basically sound. And this means that these elements here can work like fuselage elements in the structure. So if you expect some earthquake, the damage is there, then you can put under temporary safety your structure. You remove those connections, replace these elements, but the elements around are sound. Yes, this is the beauty of the dry connection. Besides being faster in execution, is that you can design them so you concentrate them, they are very easily replaceable. Yes. Well, that is the issue. Then it's a displacement demand. So you must, and this is the challenge in the connection design, is not only to guarantee the strength. I will say that guaranteeing the strength, we know how the mechanisms are. It's just interpreting the right mechanism. Is to check whether the serviceability requirements can be respected as much. So in this case, we say we expect relative displacements from the analysis. You say, I expect relative displacement of 40 millimeters. And this is an example of how you can guarantee stable. So in this case, you always guaranteed the maximum capacity. If you had some drops, you have to take the minimum load. So that is the philosophy. So you can go, then you have to see which is the demand on your connections. And is your connection able to meet that demand? And if not, how can you engineer the design of your connection so that it meets that demand? Well, I will say that we can stop here. I am open to your question now. I have spoken quite much, so we have. Well, but we have only 15 minutes. 15 minutes. I can just quickly go over that. Yeah. Okay. Yeah, it's a very beautiful topic. Yeah. Okay, 15 minutes. I go with that. So it should be like this. We go like this. Hide. Ian, I think it was in. Was this? No. Yes, it was this, yeah. Well, just a quick overview on this. So when this, concept of structural robustness started from, it started, that is the date, May 16, 1968. All structural engineers into that know that. Ronan Point collapse. Ronan Point was a building in London, it's a neighborhood in London. And at 5 o'clock in the morning, more or less, was a beautiful spring day. A lady living here, so was, I think, the third but last floor. So she had 2, maximum 3 more floors above her. So quite to the top of the building. She went into the kitchen to prepare her breakfast. She had a gas stove at that point, so she lit it. And there was this explosion because of a gas leakage. That is the result. All the corner of the building collapsed. This was a panel precast housing building. Well, the interesting thing is that the lady survived. So the explosion was not so. Obviously, she had to move to another apartment. She brought the stove with her, so the stove was not heavily damaged. But that was happened to the building. So can you imagine an explosion which does not kill the person which is there? So she was injured, burned, but she didn't die. Does not damage the equipment that exploded. Really ended up into this. So this was a case of progressive collapse because the structure was not robust. What did it happen? You imagine you have this explosion, this detonation, okay? And the weak point here were this was, as I said, the panel precast building with very weak connections between the panels and between the floors and the facade panels. So those very weak connections were the first thing to break. And you had the blowout of the facade panel. But at that point, what does it happen? If this facade panel blows out, the floor on the top loses one support. So you had this block of 2-3 stories on the top of the point where the explosion happened that started falling on the bottom floors, which were not designed for that, not only for the weight of the floors collapsing on them, but for dynamic amplification. And so you had the collapse over that. So robustness is a very specific action of the structural safety and of the structural design. And it's, the principle for which we design, which is that, accidental, exceptional loadings can happen. Absolutely, we cannot ask ourselves to design for exceptional loadings in the same way as we design for gravity loads. We have to design according to the principle that we have to expect damage, but this damage should not be disproportionate with respect to the entity of the, event which caused it to happen. You see, the Ronan Point explosion was not a big event because it was an explosion. We did not kill the person and did not damage significantly, the equipment there, but had a wall corner of the building to collapse. Well, these are some examples. When you have an explosion, the model that we use is that you have a peak. This is the detonation. So you have a burst of pressure. But then, since these are spherical waves which compresses and decompress, you have also a suction effect, and this durates much longer than these other examples. So this is a cyclic event. So the first way to, design this is to adopt some kind of, passive measures. So to adopt a structural concept that mitigates and not amplifies the effect of the explosion. If you have a building with a courtyard like this and the explosion happens here, you can expect that because of the reflection, you amplify the effect of the explosion. But then you also have other measures, structure measures, and this is the philosophy that we can use. So first of all, an indirect method. Let's use some additional reinforcement in the form of minimum tie. Or let's identify some critical scenarios. So we remove one critical element from the structure, and we design for the loads to take an alternate path, or we perform a more refined analysis where we remove the elements one by one in combination, but this requires also some kind of automatic and statistical processing. But minimum tie, you see, means that you have to tie together the floor elements, the beams, tie the roof elements to the lateral elements, tie the columns together, tie the panels together, and so on. So you really have to provide tying elements throughout all the building. And there is a criterion. This comes from Eurocode number 1, Design for Accidental Action. So there are criterion for what kind of loads I do design this. So you see here, you have the gravity loads, permanent loads. You have the variable loads multiplied by a non-contemporaneity factor. We generally use the quasi-permanent combination of action. This is the spacing of the ties. This is the length. So it's like an area of interest that they cover. You use 0.8 as a factor. Well, this is an exceptional action. Don't design that. But still, you see, you require the tie to be able to take 80% of the quasi-permanent combination of action. So it's quite demanding. Well, internal ties are twice as much the peripheral ties, because internal ties have a symmetric, generally, area of interest. And there is also a minimum force. You have load-bearing wall construction. Also, in this case, you see there is a permanent load and gravity loads, and this is the number of stories that now I will go into it, because this is just minimum tie provision. If you provide minimum tie, you don't go into that. What you can also do is you make the alternate load path, which is not exactly progressive collapse. Progressive collapse is the most refined method of analysis. But for example, let us imagine. Well, first of all, try to design your mechanism of collapse in such a way that it does not occur in this way. So this has not to be the weak point. Try to have a weak point here in the middle, so that your element breaks into two, but limits the overloading effect on the recipient floor. So this is the donor panel. This is the recipient panel. Yeah. Or have it like this. Now let's try just to make. I will make a simple hand calculation example. Okay, let us imagine that we have a beam like this, okay? And you have some loads here, which is G plus psi 2 Q, which means permanent loads G, characteristic value, variable loads Q, characteristic value. Psi 2 is the quasi-permanent combination coefficient. Okay? Well, if you design as it is, you have a diagram of bending moment like this. And how much is this bending moment here? Hmm? Yes, it's the load, gk plus C2, L square over 8. This one here. And you have this one here, this is close to k plus C2 qk L square over 14, more or less, just a number. But this just to signify you that at this central support, we have a negative bending moment. So we will expect in our reinforcement layout to have some kind of reinforcement here at the bottom. We expect some other kind of reinforcement here at the bottom. But then here, in this part here, we can expect some reinforcement at the top. Put like this, could be one or more. Okay, but then you can also have some kind of reinforcement here, tying up, or you can have even continuous, depends on the layout. But it's just to say that in the continuity support, you have negative bending moment. Okay. What if in a progressive collapse, or in simply alternate loading path method, this element here disappears? Well, you still have here gk plus psi 2 qk, and this is L, and this is L. But in this case now, your bending moment has become something like this. And this maximum value is gk plus psi 2 qk times 2L to the square divided by 8. So you have gk plus psi 2 qk L square over 2. So not only your bending moment has gone from negative to positive, but it is 4 times much larger. Really, you cannot expect to be able to design your structure to be able to resist the previous one and this one. You will have no space for the reinforcement. No space at all. So what can you do? Well, the previous situation, this one, this is the design situation. So this you have to accomplish. This is something that can happen, is accidental. But you will say, okay, I accept that this can happen. I don't design anymore my beam as a beam, but I rely upon the tie. So I accept that my beam deflects of a certain quantity, F, which I assume equal to alpha. Alpha is a number, L. Well, in serviceability limit state design, we say L over 200. Here you can accept L over 100, L over 50, so you can accept much larger. Well, and how do you resist the moment that you will have, which is what we had? Well, you resist the moment through a tie action. So your slab, which at that point is deforming very much, you go into second order, you have to accept large deformation. It becomes like a rope. The rope can only withstand tensile force. So that moment, which we said is gk plus psi 2 qk L square over 2, has to be equal to alpha L times T. So you have the force in the tie, which is T equal to the bending moment divided by, this is the deflection, large deflection that you will allow. your beam to have. And so you design your tie accordingly. So this means that you are really tying up your slab. So you are providing additional reinforcement. Additional reinforcement. It's not the one that you provide for the bending moment. So it's another one. And the most important thing is here. That reinforcement must be anchored at the edge or whatever it is, because it has really to, hang up the beam. So this is just an example, and I will just go back to the, so you see, these are the peripheral ties. You see that they are very large bars, I think, compared to these stirrups, which can be probably phi 8, these bars are at least 32 millimeters. They're very, very big bars. But you see that also to avoid the anchoring by lap and splice, you provide the couplers, so that you really have the peripheral tiles all around. So it's, not only a matter of designing for an alternative or a different structural scheme where you have removed one element or the other one, but it's also considering that your element will function in a different way. To guarantee the robustness, you do not have, or you might likely abandon the beam scheme and considering like a rope. So you are really, hanging it up. In some cases, in the panels, you can also provide vertical ties, so really hang them up. The panels in case, because you rely upon the continuous support. But if one fails, what's happened? You must have some hanging reinforcement. And this hanging reinforcement can also be, a loose one, which is mechanically anchored. You not rely upon bond, because in that case, it does not work until that moment and is immediately activated when the movement due to the loss of support is activated. So you mean what? Well, yeah, it's true, but it's also true that we do not worry most of the times, but also in that case, the structure changes. So if you lose a support, no matter whether it was dry or emulative, the structure immediately changes its scheme. So if you lose the support, no matter how it was done, immediately the beam starts working in the other way. Yes, that is for sure. But you have to check that act as a tie separately. So the issue is that you always have additional reinforcement, or you have two separate reinforcement, and one is designed only for the tie action or whatever, and the other one is designed for persistence. So the principle is, however you design it, you have to keep separate the mechanisms. So this was just to give you the flavor of what does robustness mean. Okay. Well, that's done. How we do that?